he speculates that light is an electromagnetic wave. And he is correct. We now have evidence that electric fields and magnetic fields really do exist. Because if light is an electromagnetic wave, which is created from electric fields and magnetic fields, and light exists, there seems to be pretty good evidence for it. Physicists looked at this, thought this is absolutely brilliant. However, there are some of the physics community who said that there's clearly something wrong with this equation. They do not doubt, they do not question any of this stuff. I mean, or eventually they come to accept what he has written here, but he said there's a mistake in the formula. There is something missing. What is missing from this equation that would make physicists go, wait a second, you're incomplete. There's something missing. And a clue is, it has something to do with speed.
Position.
You could get there from here, but probably not. Position is not the key there. Not the way I'm thinking of position. You want to expand?
Displacement.
No.
Time.
Not time at this point. That'll become crucial in the next thing that we do. How fast are you moving right now?
Zero meters per second.
Is she right?
No, because we're on the Earth's spinning.
Okay.
Is that what you mean?
Yeah. So were you wrong the first time you said 0 meters per second?
Yeah.
Or no? What does speed depend on?
Like relative position,
Uh,
or like the observer.
all right, relative to an observer, it's more of the velocity of the observers rather than the position of the observer, which is why when you said position, the velocity of the observer is more important. There's nothing in here about the observer. This is where some physicists, Lorentz especially, Henrik, Henrik, I believe. Lorentz, one of the dominant physics personalities, looked at this and he said, this is great work, but obviously there's a factor missing. And then he spent the next several decades trying to figure out why it doesn't show up, why the observer does not show up. And then Einstein comes along, and he says, there's no mistake here. That's the speed of light in a vacuum. The observer doesn't matter. And this is why this is so revolutionary. Set up a thought experiment. I have what we're going to call the lab frame. In other words, you're sitting on the lab here and you're just watching this happen. You have a box that is moving to the right at some speed v. It is going to emit a beam of light upwards. From its point of view, it'll go upwards. But because there's a horizontal component to it, the light's going to come up, this is a mirror up here. It's going to hit the mirror and bounce back, and it's going to get to the box over there. Because the horizontal component is the same as that of the box, and so they'll travel together. In the box frame, from the box's point of view, the light goes up and comes back. If this distance from here to here is h, and the time it takes for the light to go out and come back, I'm gonna, well, let's take a look at the distance here before we bring time into it. This distance from here to here is the same as this distance. So the distance this travel is 2 times h. So from the box's point of view, the speed of the light will be 2 times however far up to the mirror, divided by how much time it took. Over here, this distance here is h. This distance here would be half of speed times time. So this length right here, it's the hypotenuse, is the square root of h squared plus 1/2 dt, all that squared. And so from his point of view, the speed of the wave is the square root of h squared plus 1/2 vt squared times 2 over time. First off, questions about these two equations before we talk about the implications? So both of them are distance divided by time. If Maxwell did not make a mistake, if Einstein were correct, then these two speeds are equal to each other. If they are equal to each other, what falls apart? What can't be the same anymore? Let's just do some numbers. I think clearly this is longer than h. Will you accept that this is longer than h, longer than that? Yeah, that's not a trick, that is longer than that. So if this is, let's just say 1 meter, and we'll just say this is 1.5 meters. So according to the lab frame, the speed of this wave would be 3 meters, because it's got 2 of them, divided by time. And according to him, you have speed is equal to 2 meters divided by time. If the speed is the same as Maxwell predicted and as Einstein speculated, if the speeds are the same, what cannot be true anymore?
Time.
What about time?
It's not constant.
Right. That is the incredible breakthrough, the leap that he made. This time right here and this time right here are not the same. So how fast time progresses depends upon how fast you are going. I'm going to label this time down here T sub P. Oh, that's not T sub P, that's T sub P. For proper time. Proper time is the time for the observer at rest. Or, yeah, we'll go with that. I won't get into the semantics of it right now. As a matter of fact, we can calculate the relationship between these two times. So let's do it. So I have 2 times the square root of h squared plus 1/4 v squared t squared over t is equal to 2h over the proper time. I need to get rid of that radical, so I'm going to square both sides. Actually, let me get rid of 2 first. Now I'll square both sides. So I have h squared plus 1/4 v squared t squared over t squared is equal to h over tp. And, oh. I don't know how many times I've gone through this, down that path. There's, which is equal to the speed. I don't want to get rid of the 2 yet. All right, which is equal to the speed of the electromagnetic wave. The typical symbol for that speed of that wave is c. From this equation right here, from that bit, I know that h is equal to ctp divided by 2. The other equation is equal to c, so I'm going to make that substitution in for h, so I get 2 times the square root of ctp over 2 squared plus 1/4 v squared t squared over t is equal to c. I'm going to multiply both sides by t over 2, and then I'll square it. So I end up with c, well, that squared becomes 1/4 c squared tp squared plus 1/4 v squared t squared is equal to 1/4 c squared t squared. The 1/4s go away. And then it comes down to what form do you want it in. I'm trying to compare the t, so I'm going to get the 2 t terms together and then factor it out, and just I'm going to work towards the more traditional form for this. So we end up with v squared, no, sorry, wrong one. I'm not sure where it stands or that. So I have c squared tp squared equals c squared t squared minus v squared t squared, which is just c squared minus v squared times t squared. I'm going to divide by this because I want t by itself, so I end up with t squared is equal to c squared tp squared over c squared minus v squared. Multiply top and bottom by 1 over c squared. And I end up with this is equal to tp squared over 1 minus v squared over c squared. Take the square root of both sides, and I get time. The time in the lab frame is equal to the time in the box frame divided by the square root of 1 minus v squared over c squared. This is known as time dilation. Let's see what kind of impact it has. You drive to school at 90 miles per hour versus driving to school at 10 miles per hour. Does that make a difference? Will you age not as fast if you go 90 miles per hour? Will that offset the stress of running all the red lights at 90 miles per hour? Let's deal with numbers. We're going to just use the rounded off number for the speed of light at around 3 times 10 to the 8th meters per second. So let's say you're traveling half the speed of light. So 1.5 times 10 to the 8th meters per second. How much of a difference is it between these 2 times? Let's assume you're in a rocket going half the speed of light and you're in there for an hour. How much time has passed from someone who's not in the rocket and just on the side watching you go? So that time would be 1 hour over the square root of 1 minus v squared over c squared, which is basically 1/2 squared. What do you get? That, 1 hour.
1.15 meters per second?
No,
Or just seconds?
seconds, or hours. So if you're on the rocket and you've aged an hour, people who are left behind watching you go at half the speed of light have aged 1.15 hours. Biologically, you are not aging as fast as the person who's not in the rocket ship. So the people who stayed behind lost about 15% there. Imagine now you're doing 90 miles per hour, which is roughly 40 meters a second. This fraction is going to be incredibly tiny. You'd have 40 divided by 3 times 10 to the 8th, and then square that, subtract it from 1, take the square root. Most calculators can't handle numbers that small. So these are known as relativistic effects. We only care about relativistic effects when the speed is roughly, for speeds greater than or equal to 3 times 10 to the 7th meters per second. So once you get within 10% of the speed of light, then we start to care. Go under the speed of light, under 10% of the speed of light, we ignore these effects. Usually. If you think about the GPS satellites, is that redundant? S stand for satellite, the GPS? Or S stand for system? System?
Yep.
Okay. So for the GPS satellites, they actually take this into account. It's not a huge effect, but if you don't take the relativity into account, this is known as special relativity. If you don't take special relativity into account, it's going to get off by, it's either 3 meters a day or 30 meters a day. I think it's 30 meters a day. It'll be off. There's also general relativity. If that's not taken into account, that flips it the other way. But this is the only application, the everyday application I can think of where they actually take this stuff into account. But if you run to class, physically, if you have a watch, it will not be changing time as fast as if you were just walking. Now the difference, negligible, you need the multi-million-dollar equipment to notice the difference, but, and even then, there was an experiment done in the early 70s where they took an atomic clock, got them synchronized out to, I think, nanoseconds, put one on the plane, traveled around the world one way, and they compared it, and the clocks were off because of the relativistic effects of traveling at 500 miles an hour. So, that is just to give you a sense of where things are. This, I think that chapter 23 stuff blends so well, it doesn't blend into chapter 24. The derivation of the speed of light is chapter 24. Once we get that, the jump into relativity seems so natural, so we jumped out to 28, and I've introduced you to 28. For years, I then kept going with relativity. Somebody did say that it really would be nice, someone who went on to NC State said it would be nice if we covered AC, which I skipped over. So now we're going to sort of drop back, just think of this as an advertisement for relativity. We're going to drop back to do AC, and then we'll come back to relativity. Presumably we'll have time. And I hope you all have a wonderful weekend.